At the end of this video, you should be able to describe the instrument used to measure and record earthquakes, summarize the method scientists use to locate an epicenter, and describe the scales used to measure the magnitude and intensity of earthquakes. Chapter 12, Section 2, Studying Earthquakes. The study of earthquakes and seismic waves is called seismology. Many scientists study earthquakes because earthquakes are the best tool Earth scientists have for investigating Earth's internal structure and dynamics. These scientists have developed special sensing equipment to record, locate, and measure earthquakes. Recording earthquakes. Vibrations in the ground can be detected and recorded by using an instrument called a seismograph, one of which is shown on the screen here. A modern three-component seismograph consists of three sensing devices. One device records the vertical motion of the ground. The other two devices record horizontal motion, one for east-west motion and the other for north-south motion. Seismographs record motion by tracing wave-shaped lines on paper, or by translating the motion into electric signals. The electric signals can be recorded on magnetic tape or can be loaded directly into a computer that analyzes seismic waves. A tracing of earthquake motion that is recorded by a seismograph is called a seismogram. Because they are the fastest-moving seismic waves, P waves are the first waves to be recorded by a seismograph. S waves travel much slower than P waves. Therefore, S waves are the second waves to be recorded by a seismograph. Surface waves, or Rayleigh and Love waves, are the slowest moving waves. Thus, Rayleigh and Love waves are the last waves to be recorded by a seismograph. Locating an earthquake. To determine the distance to an epicenter, scientists analyze the arrival of P waves and S waves. The longer the lag time between the arrival of the P waves and the arrival of the S waves is, the farther away the earthquake occurred. To determine how far an earthquake is from a given seismograph station, scientists consult a lag time graph. This graph translates the difference in arrival times of the P waves and S waves into distance from the epicenter to each station. The start time of the earthquake can also be determined by using this graph. To locate the epicenter of the earthquake, scientists use computers to perform complex triangulations based on the information from several seismograph stations. Because computers are widely available, scientists performed this calculation in a simpler and more imprecise way in the past. On a map, they would draw circles around at least 3 seismograph stations that recorded vibrations from an earthquake. The radius of each circle was equal to the distance from that station to the earthquake's epicenter. The point at which all of the circles intersected indicated the location of the epicenter of the earthquake.
These 3 lines represent seismograms for the same earthquake taken from different locations. The primary waves, or P waves, arrived first at the seismograph stations that recorded them. The secondary waves, or S waves, arrived after the primary waves because primary waves travel faster than secondary waves. Time-distance graphs, such as this one, are used in the SP time method to determine the distance of seismograph recording stations from an earthquake. Seismologists place seismograms from each station on the graph so the first P waves line up with the P wave curve and the first S waves line up with the S wave curve. After the seismograms are placed on the graph, seismologists can see how far away from each station the earthquake was by reading the distance axis. Seismologists use distance information from a time-distance graph to plot an earthquake's epicenter. First, they draw a circle around a seismograph station using the distance from the graph as the radius of the circle. In this example, the distance from the seismograph in San Diego to a certain earthquake's epicenter is 900 kilometers. Next, seismologists draw a circle around a second seismograph station, in this case located in Palo Alto. Finally, they draw a circle around a third seismograph station located in Denver. All three circles intersect in only one spot. This spot is the location of the earthquake's epicenter, as determined by the SP time method.
Earthquake measurement. Scientists who study earthquakes are interested in the amount of energy released by an earthquake. Scientists also study the amount of damage done by the earthquake. These properties are studied by measuring magnitude and intensity. Magnitude. The measure of the strength of an earthquake is called magnitude. Magnitude is determined by measuring the amount of ground motion caused by an earthquake. Seismologists express magnitude by using a magnitude scale, such as the Richter scale or the moment magnitude scale. The Richter scale measures the ground motion from an earthquake to find the earthquake's strength. While the Richter scale was widely used for most of the 20th century, scientists now prefer the moment magnitude scale. Moment magnitude is a measure of earthquake strength based on the size of the area of the fault that moves, the average distance that the fault blocks move, and the rigidity of the rocks in the fault zone. Although the moment magnitude and Richter scales provide similar values for small earthquakes, the moment magnitude scale is more accurate for larger earthquakes. The moment magnitude of an earthquake is expressed by a number. The larger the number, the stronger the earthquake. The largest earthquake that has been recorded registered a moment magnitude of 9.5. The earthquake in Kobe, Japan in 1995 that caused damage, which is shown in your textbook, had a moment magnitude of 6.9. Earthquakes that have moment magnitudes of less than 2.5 usually are not felt by people. Intensity. Before the development of magnitude scales, the size of an earthquake was determined based on the earthquake's effects. A measure of the effects of an earthquake is the earthquake's intensity. The modified Mercalli scale, which is shown on the screen here, expresses intensity in Roman numerals from 1 to 12 and provides a description of the effects of each earthquake intensity. The highest intensity earthquake is designated by Roman numeral 12 and is described as total destruction. The intensity of an earthquake depends on the earthquake's magnitude, the distance between the epicenter and the affected area, the local geology, the earthquake's duration, and human infrastructure. At this point, you should be able to describe the instrument used to measure and record earthquakes, summarize the methods scientists use to locate an epicenter, and describe the scales used to measure the magnitude and intensity of earthquakes.